Hello and welcome everyone. This is Mr. Mountjoy. Today is Monday, so you are working on your asynchronous work today. Please follow along with the video and make sure that you have open week 14 Desmos and you're on the Engage 8.2. If you open this up and you're on somewhere else, please email us. Let us know if you're having any technical difficulties. You need to reach out to us so we can try and solve them today so you're prepared for your class either Tuesday or Wednesday. The first thing I want you to do is read through the Engage 8.2, a tessellated trapezoid, and answer these two questions using the sketchpad or the text box. You can see that there's a pattern here starting on step 0, step 1, step 2 of these different shapes and how they're changing. So we want to know how many of the smallest trapezoids will there be in step 3, so the step after step 2. And then what step will you have 256 of these trapezoids, of the smallest ones? So for example, if I count this one, 1, 2, 3, 4, there's 4 small trapezoids in this one. We want to know when is there going to be 256 of these small trapezoids. Pause the video right now and then do these two questions and come back when you're done. All right, now that you've completed the Engage, here's our essential question. When is it difficult to approximate the value of unknown exponents? When is it difficult to approximate the value of unknown exponents? So in the Engage, you probably saw that for the second question, you might think about it with exponents, and you might realize that real quickly, it's 4 to an unknown power. And you have to figure out what that exponent is. Okay, now that one may or may not have been difficult, but there are harder ones. And so we're going to go ahead and think a little bit deeper about that. What's so difficult about approximating the value of unknown exponents? So if you can't answer the next questions, at least answer this question. What's making it difficult? All right, so we still have our trapezoids, and I want you to answer this two-part question here. So at a certain step, there's going to be 262,144 trapezoids. That's a lot of trapezoids. So we don't know what step it's on. It's on a certain step. Write an equation to represent the relationship between n and the number of trapezoids. So is there a quick and easy equation that we can use to calculate trapezoids for this pattern? And then how might you find the value of that step number? So when is this going to happen? Okay, so pause the video, take some time to write an equation and see if you can find out what step this is going to happen on. 262,144 of the small trapezoids. Pause the video and we'll see you back here when you're finished. All right, so you probably realize that when you start getting into those larger and larger numbers, it's a lot more difficult to calculate the value or even approximate the value of an unknown exponent. So let's say I came up with, on the last one, 4 raised to some power is equal to 262,144. Well, what exponent makes that true? That's kind of the challenge for today. How can we figure out those unknown exponents? So this is the guided instruction. This is where I want you to follow along with me. We're on slide 5 right now. And the problem is 8.3, successive splitting. Okay, so in a lab, a colony of 100 bacteria is placed in a petri dish. The population triples every hour. So they want to know a few things. They want us to estimate or find the population for these different times. And then they want us to find the population or find the time for these different populations. Okay, so they're kind of flipping it on us. The first one, they give us the time. They want us to know the population or figure out the population. And then they give us the population and they want us to figure out the time. Now, first of all, whenever we're reading an exponential growth problem like this or a decay problem, we're looking for two things. We're looking for the growth factor and the starting spot, and they gave us both. They said that the starting place is 100 bacteria. That's what we start with in the Petri dish. And they told us how fast it's growing. It's growing at a three time rate every hour, right? It's tripling every hour. So if I were to write a function for this, I like writing functions. I think that it's helpful for understanding a problem like this. I might say, so I'm going to make sure my math type is on, and I'm going to say maybe bacteria of, and we'll use T for time, or no, let's use H for hours. So what's the population of the bacteria for different hours? And so they told us the starting place was 100 bacteria. And they also told us that this is happening, it's tripling every third hour. So there's our exponential function right there, 100 times 3 to the h power. That's all you got to do in order to write a function. You just need the starting place and the growth factor. Now that we have that, finding 4 hours, well, that's not that hard. We just need to plug in 4 into our equation. So I'm copying my equation and I'm editing it. So I'm going to change hours to 4, and now I just need to do some calculator work. And so I need to do 3 to the 4th times 100. So let me plug that into my calculator. 3 to the 4th power, 3 raised to the 4th is 81 times 100 is 8,100. Okay. So after 4 hours, our population is at 8,100 bacteria, starting with just 100. So, well, what would it be after 90 minutes? Okay, so remember our function is in terms of hours. So when I plug in H here, I need to plug it in according to hours. So how many hours is 90 minutes? Well, 60 minutes is 1 hour. So 90 minutes is 1.5 hours. So that is the number I'm plugging in, 1.5 into my function. And so I'm going to do 3 raised to the 1.5 times 100. And so after about an hour and a half, I'm going to end up with 519.6 bacteria. 0.6 doesn't make sense, so I'm going to round up to 520. Okay, so there's 520 bacteria in our Petri dish after an hour and a half. And then finally, we have half an hour. So half an hour is 0.5 of an hour, right? So I'm going to plug this in. Maybe I'll put a 0 here so it really looks like 1/2. Okay. And let's plug this into the calculator. So we get 3 raised to the 0.5 times 100. And so rounding, we get 173 bacteria. All right, so hopefully you can see that when we know the time and we don't know the population, that's pretty easy to find, right? This is just calculator work. Look at that. I know exactly what to plug in with my function. I plug in the time, plug in the time, plug in the time, and within seconds, I get the right answer, okay? Not too difficult. So finding the population given the number of hours, right? When they give you the exponent, pretty easy. Well, on this one, they gave us the population. They want to know what are the hours. So this is a little bit more difficult. So for 1,000 bacteria, this is what we're going to end up having. This is what we know. We know that we started with 100 bacteria and that our growth factor is 3, but we don't know the time. We do know that we want to know when is it equal to 1,000. So when is the population equal to 1,000? So actually, I'm gonna copy this and move it down on the next line so I can solve it. So this is an equation that I need to solve. I want to know what H is, right? So my first step in solving this equation is to we're trying to get h by itself, which is difficult, but let's just think. The first step would be to divide both sides by 100. So if I do that, I'm going to get 3 to the h power is equal to 1,000 divided by 100, which is 10. Okay. So now I need to know 3 times what, or 3 to what power is equal to h. Now, right now, we don't have a good way of doing this. We don't have an easy way to solve this. So we're just going to have to do our best. Let's think about some different options here. So our options are 3 to the first power, 3 to the second power, oops, 3 to the third power, and so on. Okay. So what are these things equal to? So 3 to the first power is 3. 3 to the second power is 9. 3 to the third power would be 3 times 3 is 9 times 3 is 27. Then it's 81, and so on. Okay. So if we want to know 10, well, we're in between these two, right? We're in between the exponent of 2 and an exponent of 3. It looks like it's closer, to the 2, because 10 is really close to 9. So we could just say a good guess is 2 point, just above 2. We'll just say that, just above 2. Okay, and that's as good as we can get right now. Like, we know it's bigger than 3 squared. We know it's smaller than 3 cubed, but we can't tell which value it is exactly. 3.2 what, right? So 3.2 something is what we're going to get here. Now that was kind of unsatisfying, right? There's a problem here. We really want to know the exact time, but we couldn't. We just got to guess around 2. All right, so that's all we can do. What about if it was going to double the population? So let me take my function again. So the next one says, what happened? When will it double? So doubling, we're starting with 100 and we want to get to 200. That would be double the population, right? Our starting population was 100, we doubled it. So again, solving this, our first step is going to be to divide both sides by 100. And so we get 3h is equal to 2. So using what we got from before, we know that 3 to the first power is 3. Oh, that's already too big. I'll throw in 3 to the 0 power up front here so we can think about what that would be. 3 to the 0 is equal to 1, right? Anything to the 0 power is equal to 1. So look at that. We know it's got to be in between these two. 2 is right in between 1 and 3, so we know it's 0 point something, okay? So a good guess is in between 0 and 1. And we don't know if it's closer to 0, if it's closer to 1, because these are kind of just really in the middle. It's hard to tell. But we know it's bigger than 3 to the 0 power. We know it's smaller than 3 to the first power. So that's the best guess we have right now. Okay. So what's difficult about finding these exponents when they're missing? When it was given to us, when the exponent was given to us, man, that was easy to find. But when it was missing, all we had was the ability to guess. We were kind of stuck there. All right, let's explore this a little bit more. All right, so we have the function 2 to the x power, okay? And we have some missing x's or some missing function values, right? So we want to fill in this table, and we know that if you plug in x into this function, you're going to do 2 to that power, okay? So the ones that they give you, those ones are the easy ones. So notice that this table scrolls real quick, so there's quite a few answers here. But if I plug in x into this function right here, for example, if I plug in 0, 2 to the 0 power, I can type in what this one is. This one's pretty easy. Anything to the 0 power is 1. Okay, so I love starting with that one. That's an easy one to calculate. 2 to the 0 is 1. Another easy one to calculate is to the first power. 2 to the first power, that's just 2. Okay, I've skipped this 1/2 because that's a little trickier. I can go on to this 2 to the 5th power. So 2 to the 5th power, that's 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So if I do that 5 times, I get 32. Okay, and I know that the box is kind of too small to fit everything, so sorry about that. All right, so let's keep on moving. So what would happen if I plug in a half? So 2 to the 1/2 power. Well, I end up, if you remember, 1/2 power means square root. So if you don't remember that, just type in SQRT, and then you can put 2. And Desmos automatically rounds it to 1.414. That is the square root of 2. Okay, so I'm just plugging in the square root of 2 right here. So I'm literally typing the square root of 2 for this answer right here. And on Desmos, if you don't remember how to do that, you just type SQRT, and then you can type 2. And then it'll automatically make it look like this, or it'll calculate it as decimal. Okay, so now that we figured that out, we found all those values. Now we want to be able to find some of these other ones. So for example, when is this true? When is 2 raised to some power equal to 4? So what could you raise 2 to in order to make 4? So you might be thinking to yourself, well, 2 times 2 is 4, so it's got to be twice, right? So to the second power would work here. And that one's just coming from memory, right? I'm just thinking about, well, I know my exponents of 2. 2 to the second power is equal to 4. Okay? And remember when we found 2 to the 5th power, we got 16 along the way. That was after 4 of them, right? 2 times 2 is 4, times 2 is 8, times 2 is 16. So I got 2 to the 4th power is equal to 16. Now we get to that one from earlier on the engage. What step will we get 256? So when will we get 256? So one of my methods is just going to be to start plugging in 2 times 2 and count them, right? So I know that 2 to the 5th power is 32. If I do the 6th power, I get 64. And then if I get double that, I get 128. That's the 7th power. And then 256. So just to double check, I'm going to type it in my calculator. 2 to the 8th power is 256. And I'm just literally on my calculator multiplying 2 times 2 times 2 times 2 and checking the answer every time. Okay, so then when will I get 1024? If I do the same thing, that's after 10. Okay, so 2 to the 10th power is going to give me 124 or 1024. All right, now these ones are a little bit trickier. When does this happen? What do you plug in for x in order to get 1/4 and 1/32? So in order to find these, I want to remind you of one rule. So when your exponent is negative, that makes it a fraction, right? So if I do 2 to the -1, that just is 2 over, or 1 over 2 to the first power, right? So this negative makes the exponent and base go in the denominator of something. So if I want it to be 2 to the negative what power is equal to 1 over 4. So if we think about what is 1 over 4, we already found what equals 4. When you have an exponent of 2, you get 4. So this is 2 to the second power. So it's in the denominator, so I want a negative 2 here. So my answer for this one's going to be negative 2. Okay. And then when do I get 32, right? I need an x or a denominator of 32. So that remember happens over here at 5. So when x equals 5, we get 32. So when x equals negative 5, we're going to get negative, or 1 over 32, sorry. Okay, so we get 1 over 32 when the exponent is negative 5. All right, so we got a pretty good start here. This next one here, I want you to pause the video and go ahead and try on your own. So we have x to the 5th power. We're trying to fill in these values here. So go ahead and pause the video and see if you can come up with those. And then when you come back, I'll have the answers for you. All right, welcome back. Hopefully you were able to figure these out. Let's go ahead and check your answers real quick. So on the first one, if I want an exponent of, or I want the 25 in the denominator, I need to square x and make it negative. So x to, or 5 to the negative 2 is 1 over 25. 5 to the negative 1 is 1 over 5. Anything to the 0 power is 1. The 1/3 is a trickier one to write out, so I just want to spell it out for us real quick. So what you're going to type into the calculator, or for this one here, is you're going to type in nth root, and then that's going to give you something that has a blank right here and a blank right here. And so when you click, you're going to type in 3. Or if you're already on there, so after you type in nth root, you're going to type in 3, and then you need to hit the arrow key, and then you can type in 5 for your base. And so this is the cube root of 5. And so that is about 1.71. This one is the square root, right? So we can just type in SQRT of 5, and that'll give you this one, because anything to the 1/2 power, you're square rooting it. 5 to the 1st power is 5. 5 to the 3rd power is 125. 5 to the 4th power is 625. And then 5 to the 5th power is 3125. All right, so that's it for guided instruction today. That's how we fill out these missing tables. I want you to quickly think back. What's the hard part about approximating unknown exponents? So what was hard about calculating these missing exponents, this top row? What's so hard about it? What makes it difficult? Okay, we're going to explore this more in the next coming lessons. Is there an easier way to figure out what these exponents are? Okay. If you haven't already, make sure that you fill in your guided instruction on Desmos, so that way we know you're ready for the practice problems on Tuesday or Wednesday. And then if you haven't already, the quiz is due by 10 p.m. tonight. So make sure that you get that quiz done before tonight at 10 p.m. All right, everyone, have a great week. We'll see you later.